part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing the motion of a charged particle in an otherwise uniform magnetic field. We'll be making use of the Lorentz Force Law, the justification for which lies in experiment. Lorentz Force Law tells us that the force on a charged particle in the presence of the magnetic field is equal to the charge times the cross product of the velocity in the magnetic field. So this is a very different expression than from the one that we use in electrostatic force. Their force is equal to charge times the electric field. Here you see that the force is actually perpendicular to the magnetic field, and not only that, the particle has to be in motion in order for it to experience magnetic force. Let's do the simplest problem using this, and that is a cyclotron motion. In this case, we'll assume that the particle, is charged, whatever, has a velocity vector perpendicular to the magnetic field and no component lying along the magnetic field. So in other words, let's suppose that the magnetic field lies along the z-axis. Okay, so our force can be written as mass times the derivative of the velocity with respect to time, and I'll break that down into components. Now, assuming that the particle has velocity in the x or y direction, or some combination, broken down into components, we have mass times the derivative of the x component of the velocity with respect to time is equal to q times y component of the velocity times v. Then we have mass times the derivative of the y component of the velocity with respect to time is equal to minus q times x component of the velocity times v. And then finally we have mass times the derivative of the z component of the velocity with respect to time is just equal to 0. I'm going to forget about the z component. I'm just going to assume that there's motion in this in the xy plane only. I'm going to rewrite these to make the notation a little more convenient. If I divide both sides through by mass, I have a set of coupled equations. So the derivative of Vx with respect to time is equal to QB over m times Vy, and the derivative of Vy with respect to time is equal to minus QB over m times Vx. I'm going to introduce a new symbol here, and this is the cyclotron frequency. and that's equal to the absolute value of Q times B over M. Now notice that I'm defining the cyclotron frequency such that it's always a positive number, which is why I use the absolute value signs. Therefore, when I rewrite my couple equations, by replacing QB over M by omega C. Now notice I have a plus and minus sign up front here, and the minus and plus sign down here. Well, that's because the cyclotron frequency is defined to be a positive number, so we can't lose track of the fact that Q might be a positive or negative. So that's why we have a positive up here, negative down here, and then it's reversed. So the positive, or the symbol on top refers to the positive charge, the symbol below refers to the negative charge. So how I solve this equation is that I'm going to take the derivative again of both sides. And I'll write this first one, I'll substitute in for what v dot y is using this expression. So we have second derivative of Vx is equal to plus minus times omega c, the cyclotron frequency. Again, plus refers to a positive charge, minus refers to a negative charge, and v dot y is equal to minus plus omega c vy. So whether you have a positive or negative charge, you're still going to wind up with minus omega squared vy, and that should be the x there. Okay, so all I did was I took the derivative of both of these equations again, and I substituted in for v dot y. I have plus minus out here, minus plus omega c dx, and that just leads to a minus sign whether the charge is positive or negative. I'll do the same thing for the second derivative of vy. That's equal to minus plus omega c plus minus omega c vy, and we have two sets of couple equations. Pull them apart such that we have first equation is in Vx, the second equation is in Vy. Well, this is an equation of just a simple harmonic oscillator, so therefore Vx has a formula with some constant C1 times cosine omega c times time plus C2 sine of omega c times time, and similarly for Vy. We have two different equations, different constants, because it won't necessarily be the case that C3 is equal to C1 or C4 is equal to C2, because we need to look back to this, these two conditions, and I can use either one of them. So let's suppose I invoke this first condition, that the first derivative of x with respect to time thus has to be equal to omega c times Vy. Being careful to retain the symbols for plus and minus charges. And for now, I'm going to restrict my attention to positive charges. So therefore, find that C4 is equal to minus C1, and C3 is equal to C2. Leave it up here for a minute, because unfortunately I'm going to have to erase some of this. Now solve for the velocity. I want to know what the trajectory looks like, so I'll have to integrate this expression once again. First, it might be useful to specify some initial conditions. So in other words, let's suppose at time equals 0, Vx is equal to 0, and Vy is equal to V perpendicular. So this is the speed of particle. So all I'm saying here is that some time t equals 0, the velocity is only in the y direction and it has a speed, V perpendicular. See immediately this term will drop out as this one will. So I'll be left with, if I choose C1 is equal to 0, then this first term will vanish. Second one vanishes automatically at time is equal to 0. This term vanishes automatically at time is equal to 0. And therefore we'll be left with C2 is equal to V perpendicular. So therefore, the x component of the velocity is equal to the speed times cosine omega c times time. And that should be sine omega c times time, and this will be okay? Now I want to know what is the trajectory. So if I integrate this once more with respect to time, I'll give me another constant x naught. This first term will give me cosine omega c over time so minus v perpendicular minus the speed of the particle over the cyclotron frequency. And in the y direction, I'll have y minus y naught is equal to the speed of the particle of omega c times sine of omega c times time. These two equations trace out the motion of a circular orbit, or in other words, cyclotron motion. The The motion is centered about some position, x naught, y naught, and that's called the guiding center. So making a sketch here at time equals 0, x minus x naught is equal to minus v perp over omega c, and y minus y naught is equal to 0. So in other words, you're going to be to the left, over here. Velocity is going to be pointing upwards at this point. And this particle, positive charge, will travel in a clockwise direction. Okay. Now I'm going to introduce yet another symbol, and we'll call that the Larmor Radius. And that has the value of the speed of the particle over the cyclotron frequency. So what happens when you have a particle that has some initial motion that is perpendicular to the magnetic field, the magnetic field causes it to turn. So if this particle has no initial velocity component along the z-axis, in other words, along the direction of the magnetic field, it's just going to circle about. In the case of a positive charge, if the magnetic field is directed out of the board, positive charge will travel in a clockwise direction. A negative charge will travel in the opposite direction. And what you'll see is that you'll wind up with a set of equations that looks virtually identical, only we'll have the minus sign left off. So in other words, at time equals 0, assuming you have the same guiding center, you'd be over here, but then your velocity vector would be pointing upwards and the motion would be in a counterclockwise direction. So charged particles travel in such a way that they tend to diminish the imposed magnetic field. We haven't talked yet about what or how magnetic fields arise, but we're assuming that we just have a uniform magnetic field at first. But the fact of it is, a positive charge will travel in a clockwise direction, a negative charge will travel in a counterclockwise direction, and both of them will tend to diminish the imposed magnetic field. That kind of behavior is called diamagnetic, and plasma particles tend to behave that way. Okay? Now let's suppose that we have an additional complexity here. So let's suppose that v is equal to vx in the x direction plus vy in the y direction plus vz in the z direction. Now when I look at v cross v, I'm still going to get the set of equations I got before for that part of the circular motion. However, the particle has an initial component in the z direction. So in other words, when we write down our force equations, and resolve them in components, x and y components will be the same as before in the z direction. You'll still have mass times the derivative of the z component of velocity with respect to time z equals 0, but this time you have some initial component. So what happens is that your particle will travel about this center, but there will also be a velocity component, so it will spiral outwards. So in other words, it will trace out the trajectory of a helix. So here's the thing. Magnetic fields can't speed up or slow down particles. So magnetic force does no work on charged particles. Can turn the orientation, as we see here, the cyclotron motion, or with helical motion, but it can't speed up or slow down. We need to have some other force, another electric force to do that. Next example I'm going to work, we will add an extra force. We'll add an electric field. So then your Lorentz Force Law will look like this. It's charge times electric field plus charge times cross product of the velocity vector and the magnetic field. I'll assume here that there's, in addition to a uniform magnetic field in the z direction, an electric field that has a component both in the z direction, parallel to it, and also perpendicular to it. And B cross B. And we'll be left with the same two terms as we had in the previous example, because any component of the velocity that's perpendicular, or parallel rather, to the magnetic field, when you take the cross product of it, that contributes nothing. I'm going to write out each of the components of the force. In the first case, we consider the x component, and there is no x component of the electric field, only a y and z component, so we wind up mass times derivative of the x component of the velocity with respect to time is equal to q times vy times b, the magnetic field. The y component, right hand side, we have minus q vx times b, and then we also have the effect of the electric field in the y direction as well. And in the z direction, the z component of the force is equal to q times z component of the electric field. And once again, I'm going to make the substitution that omega c is equal to qv over m. And remember, we take the absolute value of q because we've defined the cyclotron frequency to be a positive number. And that requires us to put a plus and minus sign out front to distinguish between positive charges and negative charges. And here I'm multiplying and dividing by b so I can factor out cyclotron frequency from the drift term. I'll tackle the z component first. That's the easiest one because that is not coupled to either of the other equations. integrating it once yields Q times EZ over M times time plus V naught Z. And integrating once more. We wind up C naught plus V naught Z times time plus QEZ over 2 M times T squared. So if there's a Z component of the electric field, the particle will accelerate in the Z direction. If there's no Z component of the electric field and there's just an initial component, well, then you're going to see it traveling at a constant rate of speed in the Z direction. Okay? And of course, if there's neither an initial velocity nor an electric field, well, Z will be what it started with. Okay? So now let's focus our attention on these couple equations here. I'm going to proceed the same way as I did before. I'll take the derivative of both sides. And here the second term drops out because this is constant. We're assuming both a uniform electric and magnetic field, and the cyclotron frequency, of course, is constant. Substituting for V dot Y. And over the right-hand side, you have plus times minus or minus times plus. So whether it's a positive or negative charge, that's still going to lead to a minus omega squared term. Put it over the left-hand side, that becomes positive. And over the right-hand side, we have plus plus times minus minus or minus minus, and that's omega c squared EY over B. In the y direction, we'll have exactly the same equation as before. So the effect of this electric field that has a component perpendicular to the magnetic field in the y direction leads to an additional term. So we have an inhomogeneous equation. And I'm going to solve this. Dx is going to be C1 cosine omega c times time plus C2 sine of omega c times time plus EY over B. And in the bottom we have C2 times cosine of omega c times time minus C1 times sine of omega c times time. And remember, when you integrate it, the constants aren't necessarily going to be the same. In fact, they're not. But we apply these conditions that the first derivative of x is proportional to Vy, or vice versa, plus an additional term. Anyway, this is the upshot of those equations and conditions. Okay, I'm going to apply different initial conditions from the previous example where we were just investigating cyclotron motion. And I'm going to assume that Vx, Vy, Vz are all equal to 0 times 0. And furthermore that x, y, and z are all 0 at time 0. So in other words, we're assuming that at time 0 the particle's at rest and it's at the origin. Okay, so in the first case, applying the condition that the velocities vanish at time 0, we wind up with C1 is equal to C1 plus Ey over B. Second condition, Vy vanishes, gives us C2 is equal to 0. Sign terms automatically drop out at time equals 0. And therefore C1 is equal to Ey over B. And now I'm going to integrate these one more time to figure out equations of x and y as a function of time. Now we have initial conditions, and x and y naught have to be chosen such that x and y vanish. In the first case, at t equals 0, both of these terms vanish, so therefore x naught is equal to 0. And in the second case, this has to, y is equal to 0 at time 0. So therefore, y naught is equal to Ey over omega b. And this is the equation of a cycloid. And we also said if there was a z component, you'd have this additional term as well. But I'm going to assume that EC is equal to 0 for now. So we'll forget about this and just focus on these two equations. What you'll see is the particle starts from rest at the origin. There's a component of the electric field upwards, so the particle will accelerate. But as it starts to accelerate, it gains velocity, and the magnetic field will cause it to turn. So we'll see motion like this. So it's speeding up, and then it's going to travel against the electric field. The electric field is still directed upwards, but the particle's motion is downwards, so it's slowing down. It'll come to a rest there, and the whole process will repeat itself. This is a cycloid. And the strange thing is that even though there is not a component of the electric field in the x direction, that's the way the particle drifts, okay? Another point I wanted to make as well about this term, this drift term, there's no dependence on the charge. So it doesn't matter whether it's an electron or an ion, it's going to travel the same way. There's going to be the same overall drift to the right. It doesn't matter how big the or what mass the particle has. It also doesn't matter how fast the particle was traveling initially. So what was its speed in the xy plane? It makes no difference. This drift is simply EY over B. Okay? And it's also possible to handle problems of this nature if you didn't have an electric field. Let's say you had a gravitational field instead. What you'll see is that there will be a drift of the guiding center. We barely just scratched the surface of the kinds of motion or trajectories that can be investigated. We've assumed that the magnetic field and electric fields are uniform. Generally speaking, of course, they're not. The electric field might have dependence on position. It could be, have a perturbation to an otherwise uniform field. It could vary in time. The magnetic field might have a gradient to it. People in the plasma physics business investigate that kind of motion, and as I said, life gets very complicated very quickly, and for now we've just focused our attention on cyclotrons, helices, and also cycloids. If you're having trouble visualizing this, I urge you to check out the simulations I posted on the BocaPhysics website. I do have a cycloid motion, I have cyclotron motion, and I have helical motion as well.